Okay, so we've done enough content, right? I've thrown enough at you. Let's talk a little bit about the exam, about what you might find, any advice that I have to do well on the exam, although you could summarise that with the word up there, and that's about it. Then we're going to go through a past paper, right? Because obviously no one's emailed me with topics because none of you have looked at the topics yet because it's not been Easter, right? I know this, I'm not an idiot. So we'll have another revision lecture after Easter where maybe I can answer some targeted questions. If people email me questions, I might anonymise those answers and put them on like a frequently asked questions or something on Moodle. I do that from time to time. But I won't ever like say, so you can feel free to email me questions and I won't ever say this person asked this question because everyone always has the same questions anyway. All right, so we'll talk about the exam. I am recording. Right. Structure, what it looks like, that kind of thing. Exam techniques, past papers, this kind of business. And then we'll just do some revision by answering one of the exam papers, right? Perhaps last year's or the year before, seeing how we get on. Right, that's assuming I remember the answers. Okay, so the exam, right? This is only a 10-credit module. So the exam is 60 minutes long, which is not that long, right? But that also means I can't ask you too many long answers. It's 3 questions, all mandatory, right? Not all of the past papers are structured that way because this module has evolved over time, right? And also, I wasn't teaching it 5-6 years ago. So each question is worth a third. And in general, the question 1 is kind of a pick and mix of random topics from about the course, and questions 2 and 3 will be on more specific areas. For example, networking, or software and operating systems, or cryptography, or something like that. Right? And if you look at the past papers, you'll get a good idea of the kind of questions we're talking about, right? And also quite a good idea about what's not on the exam, which I'll mention in a minute. Right? Not everything is examinable, and I'll draw attention to those things, right? But most things are. Okay. Crucially, there won't be any maths at all. Right? I'm not going to ask you to do any maths. I'm not going to ask you to implement any cryptographic ciphers or, you know, encrypt this number using RSA where your n is 167 or something like that. I won't ask you to do that. Right? But you might need to know how RSA works. So you need to understand how cryptography works, but not actually be able to run through it on a piece of paper, I guess. Right? But if we do a past paper and we get to a cryptographic question, you'll see the sort of answer I'm looking for. Okay, so what's on the exam? Well, that's a shame. Not most things, right? Most things are examinable. Any topic I've covered in the lectures. Okay. I know that I like to talk around a subject. That's how I do things, right? Frilly stuff that I've said in passing probably isn't on the exam, but I would ask me if you're unsure. And also, bear in mind the past papers, right? And I'm going to list a few things in a minute. So everything is theoretically examinable except for these topics, which I found that are not, right? Again, if in doubt, just ask me. Okay, these things are not on the exam. So Galois counter mode is not on the exam in any level of detail beyond the very simple slide that I showed that just shows that it exists, right? Other modes of operation are on the exam in the sense that I would like you to be able to explain to me, for example, what the difference between electronic code book and cipher block chaining is, right? If you don't know what those two things are, that's why you need to do some revision. Right? The mathematical proof of RSA, which is on the slides because I put it on for a laugh, right? That is not examinable because I couldn't tell you what it is off the top of my head. Any applied cryptography, you don't have to do cryptography, I already said this. Okay? Any detailed historical account of like worms and viruses and when AES was ratified and when the data encryption standard was deprecated and when TLS 1.1 came out and things like this, right? I'm not interested in your knowledge of dates. This is not a history module. Right? I'm interested in what is it about TLS but interesting from a security point of view. Right? So there won't be any questions and you won't see any questions on the exam, on the past papers of that type. Right? So understand what a virus is, or a worm is, and you know how they operate, but you don't need to say when the Morris worm was written and what that specific worm did. Right? That's just for interest. Right? The names of specific CPU registers like sysenter, right? I'm not going to need you to remember that. And any writing of IP tables. We've done plenty of that in the labs. We're going to call it a day on that, and let's hope we never have to do it again. Right? Except for me, who has to do it every year. Okay. In terms of further reading. Right? Theoretically, everyone says that all core textbooks are examinable. Right? Now that's ridiculous because they're huge. Have you seen the Ross Anderson textbook? But also, on the other hand, they are quite interesting reads. But my advice would be that they're not examinable unless it's related strongly to what I've talked about in the lectures, right? So if you want to read the Ross Anderson textbook, the chapter on cryptography, you'll learn a lot more about cryptography and probably do better in the exam, but you don't need to learn about things like the random oracle model and linear and differential cryptanalysis because I chose not to cover those things. Okay? So you'll get to these things in a chapter and you'll go, oh, I don't need to read about that, but you can anyway because you're super interested in it and you will do, right? Of course. So just, yeah, read around by all means, and the Goldman text has got a lot of good stuff in it, but bear in mind that if I haven't talked about it in the lectures, if there's not at least a slide on it, it's not going to be on the exam. Right. Okay, now, the very best way of working out whether something could be on the exam is to look at the past papers, right? It's not because I endlessly reuse questions, it's more because that's how I write exam papers, so you can see. Right? And there's at least 3 or 4 now exam papers that I've written going back recently, and then beyond that it's other lecturers, but they are similar-ish. So what I've done, as I mentioned this in the other lecture, is I've gone through and I've annotated. Who knew you could annotate PDS? I didn't know that. Right? Annotate PDS with red things, that means you can ignore that question because it makes no sense because I haven't taught it. Right? So I've basically tried to mark up the exams a little bit so that you can focus in on what you need to know. Right? Because crazy as it might seem, I don't want everyone to fail. Right? I have to answer questions from higher ups if that happens. And also, I want everyone to know about security. That's my job. It's not to get you past an exam. Right? So the more you learn about security, the better it is for me as well. And it seems to me that if I can draw your attention to the kind of questions I might ask, and that means you actually learn that stuff, that's a win for me, right? Rather than just everyone gets a good mark on the exam. So everyone wins. Right? That's my goal. Okay. So how do you do my exams? Well, let's have a quick look at one. So let's have a look at this one. So this is one of my exams. This was from last year. Right? It looks like all the other exams you've seen since you started university. So you've got one question, which we'll go over in a minute, on general computer security, which could have stuff from a variety of places, right? And I've annotated where, for example, we did Tor this year, whichever year this is, and this is the year before last, actually. We haven't done it this year, so you don't need to answer that question, because I'm not going to ask it. Right? I'll talk about these in a minute. But the point is you've got 4 questions, each of which this sums to 20 marks, and then you've got another question which happens to be on, I don't know, network and internet security in this case, so you've got kind of those kind of questions on this one, and then you have a cryptography question down the bottom, right? I like cryptography, as you know, there will be a cryptography question. I don't think you can just get lucky and I'm going to skip it. So, yeah, I would focus on that a little bit. Right, but because you've not got optional questions, you have to kind of cover most of the material, right, inevitably, or you run a risk. So, let's go back to here. Right, I'm not going to give you too much advice on how to do the exam because obviously you've done these before. Right? Everyone knows how to do it, you're all doing fine. So, because everyone has their own technique as well, right? Everyone does the exams differently, prepares for exams differently. When I was a student, I revised for exams in a different way to other people, right? And that's just how it is. Right? All I would say is that you've only got an hour, right? So I'm never going to ask you to write too much for a question, right? The most marks you're going to get for a question is maybe 7 or 8, and that's really looking for key points on things like cryptography. It's not looking for you to write essays on stuff, right? So if there's a question for 4 marks, I wouldn't expect you to write more than half a page for that, maybe less, right? Because that's quite, 4 key points, get them across, and that's all I need. Right? It's much easier for me. I mean, you can write bullet points if you want. That's great for me, much easier to mark. Right? As long as you mention the points, it's all good for me. And basically, do some revision. Right? It's linearly correlated how much revision you do with how well you do in the exam, almost certainly. Right? I wanted to show you this. I'm not sure if I should show you this, but I'm going to. It's not the exam, and it's not something dodgy, don't worry. This is the frequency of all the marks from 2015 to 2018 on this module. Right? This is just for the exam. Right? Now, people don't usually show you this, but I think it's quite interesting. Historically, the university... Oh, it's not there, by the way. That's why you see nothing. I know that. It was by design, so that you wouldn't all get distracted and stop listening to me. Now, historically, the university has always argued that marks should average 60 and then have a normal distribution. Right, which means that people get somewhere above or below 60, depending on how much revision they did. That is not what really happens, right? You have like a bi or tri or quad modal distribution, depending on the class of people you're thinking about. Basically, the people who've done loads of work and the people who never turned up to any of the lectures, right, are two different things, right? Which is why it looks a little bit like this. So you can see that the average for the exam, bearing in mind the average for the coursework is slightly higher, right? So the average for the module is somewhere just above 60%, right? Is about 58%, something along those lines, right? And you can see there are plenty of people who get into the 80s and 90s. So it's very possible on this module to get an extremely high mark because the answers are very, there is a right answer to all of my questions. It's not up for interpretation a lot of the time, right? And it's also possible to do really quite badly, right? If you do what someone did and just draw pictures on their thing instead of answering any of the questions. I mean, it was interesting to look at, but I couldn't award any marks, right? So what actually has happened here, but this is not a unimodal distribution. What's happened, in my opinion, is, and this is just my opinion, is that you've got people who engage with the course up here, and then you've got people who kind of sort of maybe did and read it at home, and then you've got the people who didn't engage at all, right? As a teacher, this is not surprising to me at all, right? There are people who I've never seen before on this course who will turn up to the exam and do it, and they'll be down there because they haven't done anything, right? And they're not going to suddenly know how RSA works. Right? So my strong advice would be to do some revision, right? Because you'll be up in this black area up here, which is where you want to be. Good, okay. So if you want a super high mark, maybe, do that. If you get stuck, ask me some questions. There's some extra videos on Moodle for the really hard cryptography stuff to do with Diffie-Hellman and RSA. You might like to watch them or just watch the lectures back. Really up to you. Okay. So, we've got a little bit of time. Let's answer some questions. It's on there, that's why it's confusing. Right, it's going to be slightly difficult for me to do this because I'm not looking at... Hang on, let me see if I can duplicate the screen. There we are. Okay. Right, I won't answer the Tor one, although Tor is really interesting. Right, can everyone read that? I can try and make it a little bit bigger. Maybe. Yeah, it's pretty... Oh, no, it's too big. Too far. Okay, okay. All right, so let's go. So, what is a stack canary? What does it attack against? What attack does it protect against? Right, this is only 3 marks, so I'm not looking for too much detail. Right, what is a stack canary? It's a random number placed before the return address on a stack when you make a function call. Right, and then, when you return from the function, you check that value to see if it's been altered, and if it has, you throw an exception. Right, and the reason you do that is because it means someone's performing a buffer overflow. So it protects specifically against stack buffer overrun attacks, stack overflow attacks. Not stack overflow, stack overrun attacks. Right? 3 marks, job done. Right. That would take you like 2 minutes to write. That's problem solved. Okay. If any of you, so I'll go slower on the harder questions. By the way, I'm not just going to blitz through them and hope that you can remember it. Right. Okay. This question, you might notice if you look through the past papers, does come up from time to time because I kind of feel it's a bit of a staple. So define the 3 components of a CIA model of computer security. So that's confidentiality, integrity, and availability, yes, not authenticity. Don't write authenticity. That's not the answer to that question, right? Someone always writes that. Okay, 6 marks. So, 3 components, define them, that's done, right? You need to define them, not name them. So, confidentiality is the idea that we keep our information away from unauthorized users. We prevent unauthorized access to our information, right? Integrity, we prevent unauthorized altering or manipulation of our information. And availability, we prevent the unauthorized withholding of information, right? Or something along those lines, okay? Give one example of an attack that might seem to break each component, right? So I'm not looking for databases. If you just write the word databases what? Right, that's not an attack, that's a something else, right? So be specific, but you don't have to be verbose. So just say, a confidentiality, right? Stealing someone's encryption key and decrypting their email. Right? I'm not looking for something super clever, I'm just looking for something that's the answer. Right? Integrity, right? Flipping bits on a stream cipher that's not protected by a MAC. Right? Or hacking into a database and altering medical records. Right? Just a little bit more information so that I know what you understand what it is. Right? And availability, denial of service attack. Right? Denial of service attack on a specific website if you feel like being a bit more explicit about it. Okay? So yeah. Try to remember what the CIA triad refers to, because really the one kind of theoretical definition of security that I think is really important, because it gives you those kind of 3 things you're trying to get from most of the stuff we've learned about over all these lectures. Okay. When user authentication is required, passwords are traditionally stored in a hashed form in a database. Yep. Briefly outline the principles of offline password cracking based on dictionaries. How does password salting make attack more challenging? Okay, so there's really 2 parts to this question. One is go over dictionary attacks, and one is talk about salting. Right? So notice I'm not talking about brute force password cracking, right? Because it's not in the question. Right? So the marking scheme will be explicitly about dictionary attacks. So the idea of a dictionary attack is we take a dictionary of common passwords or common words or whatever we want, right? And we hash variants of these, right? Or we hash them, and we compare those hashes with the hashes of a bunch of passwords that we've got. If they match, we know we've guessed a password and we can crack them that way. Right? We might also apply rules to manipulate those passwords to make the attack more effective. Right? Another alternative is you can combine dictionaries together like this so that you get combinations of words. Right? Just describe to me how a dictionary attack works and what it's for is how you're going to get these marks. Right? Now, salting. What difference does salting make? Well, a salt is a random string that you append to a password or prepend to a password before you hash it. Then you store that unencrypted next to the hash. And the reason you do that is because then it stops people with the same password having the same hash in the database. So imagine that you've got 10,000 users' hashes, right? And if you're not using a salt, then some of those hashes are going to be identical. And as soon as you crack one of their passwords, you've cracked all the others by definition. Right? Because if their password's a password, then all those hashes are going to be exactly the same. If you use a salt, every single person's password is different, but their hash is different, even though their passwords might be the same. And really, on a simple level, what that means is when you're brute forcing through them, you're going to have to try every combination of word and salt. So if you've got 10,000 users with 10,000 different salts, to try and guess the word password 1, you've got to hash that 10,000 times, not one time. Right? That's a huge undertaking. Right? So it massively slows down attacks on multiple users' passwords. Right? The only thing to mention, maybe, is, bearing in mind I can't remember what the mark scheme is for this, but it seems like the sort of thing I'd write, is that if you have only a single user you're trying to break, assaulting has no effect, right? Because you just automatically append it to every single password. The hashing doesn't slow down at all. Right? You get a minor inconvenience of having to append this string, but that's it. Right. Okay. So, that's the sort of general question. What we'll do is we'll start working through this exam, and then if see how we get on, maybe we'll look at the next exam. Right? Try and take home a bit of the sort of thing. Yes?
Did you say that you could keep the salt separately to add a bit of security?
What, you mean like a level of indirection?
Yeah.
Yes, you could say that. Right? So it's not typically done that way, but I suppose a bit like key encryption keys, you could put it in a different table and it would make it slightly harder to break. Yeah? Yeah. You might find yourself with an extra mark for that. I couldn't tell you until I looked at the mark scheme.
Couldn't salts be randomised with some of the user data to make them more effective with their individual user passwords?
So the best possible salting approach is going to be random per user. Right? So you could base it on the credentials of the user or the name of the user or something like that if you wanted. Some previous implementations of salting just used like 10 salts, right? And so each user had one of the 10, and that only slows down your attack by a factor of 10, not a factor of 1,000, right? There's not really any benefit to making the salts hard to guess. It's just that they've all got to be unique. Right? That's really important, because the more unique they are, the less you can kind of skip steps when in the brute force. Does that make some sense? Yeah. I mean, actually, it would be quite easy to just base assaults on let's say someone's username, like a hash of it, and that way you wouldn't have to store them in the database, theoretically. Yes? Very good, yes. So I'm not sure whether I want any reference to rainbow tables in this answer, because I've mentioned mostly about dictionary cracking. But yes, salting does specifically basically completely kill rainbow table attacks. Rainbow table attacks are where you can pre-compute all these hashes and just store them on a big disk, and then just look through the disk, right? So essentially your cracking then becomes an offline search through a table rather than a actual hashing operation, right? And it means you can, bring some massive server to bear on calculating all these hashes ahead of time and then just store them on a disk and come around later, right? This was very easy to do on Windows XP. I've done it on Windows XP before. Someone I worked with forgot their password. There was a reason I was doing it. And yeah, it took like 2 minutes to break with this rainbow table. So salting stops this because you can't possibly compute the rainbow table for all possible password combinations and all possible salts, right? Also, what's hurt rainbow tables is the fact that now passwords can typically be much longer, right? So hash lengths are longer. This was more of an approach when maybe there was only 2 to the 8 different kinds of passwords you could pick, and then you could hash them all and store them on a disk. Okay. Anyone else, any questions? Please do ask, or else we'll continue scrolling. Right. Oh, there's more. Okay. Right, this protocol downgrade I've kind of mentioned in a little bit. I probably wouldn't, worry too much about a huge amount of detail on protocol downgrades. But the idea of a protocol downgrade is, I'd have to look back at the lecture to remember whether I talked about it or not. The protocol downgrade is when you're performing a handshake, let's say a TLS handshake, right? And what we know is about TLS is that 1.2 and 1.3 are pretty secure, but SSL3 is not secure at all, right? And so if you can trick the client and the server into having an SSL3 connection rather than a TLS 1.2 connection, you can significantly weaken their encryption and the ciphers they use and the protocol they use, and then perform a man-in-the-middle attack. Right? So the idea of a protocol downgrade is to intercept those initial client and server hello messages and alter them in such a way as to convince them that one or the other doesn't support TLS 1.2 or something like that, and they only support SSL3. Right? And if that happens, then they go, well, it's better that we use SSL3 than we don't have a communication at all, and so maybe we'll just use it. Right? And that's when you do an attack, right? Because SSL3 is weak. Okay? Now, there are some methods. So I've just provided one example where this might lead to a vulnerability. Right? If you can trick a server and a client into using SSL3 or TLS1 rather than TLS 1.2, that's going to be a big problem, right? Because they might rely on shorter RSA and Diffie-Hellman parameters, or they might rely on flawed protocols where, for example, they don't perform a message authentication over the entire handshake, right? Which is a way of making sure there's no men in the middle. Okay, so that's what a protocol downgrade attack is. Now, theoretically, any protocol where you discuss what you're going to do and then do it is vulnerable to this kind of attack if it's had multiple versions, right? This question hasn't asked how you prevent a protocol downgrade from happening. But in general, what you do is you make sure that you aren't able to operate SSL3 or anything like that. So you, for example, have your server set up such that it won't make SSL3 connections. If a client comes along and for some reason it looks like all they support is SSL3, you drop the connection and don't talk to that client. Right? And you send them a warning that says, sorry, you're going to need to upgrade from Internet Explorer 6. Right, that's kind of the idea. Okay. So, if an attacker discovered a weakness in a website that permitted cross-site scripting attacks, how might they exploit this to steal user cookies? Right. So, a cross-site scripting attack, recall, is when you embed some kind of HTML or JavaScript into a user field of a website, and what that means is that when that page is then served out to other people, their browser interprets this as a script that needs to be executed and runs it. Right? So the first part of so this weakness in the website is going to be, some user entry area where you can then serve that back out to other users, right? Or you could talk about a reflected XSS if you wanted. Either of those would be fine. A reflected XSS is where you reflect something from the URL bar back into the HTML. Right, and then you can trick a user into clicking that link. So let's imagine that you put a script tag into some user form which then got presented to other users, right, in a persistent XSS attack. Right, you will steal user cookies by calling document.cookie or similar and extracting the cookies for that session. You would then need to have that script dial out to your server where you would then log that cookie and maybe where it came from. Right? I'm not looking for much more detail than that. Certainly don't write any code, crikey. Okay. Now what could you do with cookies once you've stolen them? Well, think about, if a cookie is used for some kind of persistence on a website, then you can hijack that session. Right? That's the kind of language I'm looking for. So if they've clicked keep me logged on, or they're halfway through a bank transaction or something like this, then they're going to have cookies which represent the state of their session and essentially their authentication token. Right? If you can have those cookies, there are programs you can run and plugins for things like Firefox where you can say, I want to go to this website and I want to use these cookies here, and it will do it for you, right? Even if those are not your actual cookies. Okay. So, yeah, that's about it. Any questions about XSS? We covered, yes?
So can JavaScript take cookies of any website or just the site? So like if I'm running click on a specific domain, can I grab cookies of other?
No. You can't grab, so, no, almost certainly not. Right? The Chrome and Firefox and Co., if they've been coded properly, they won't allow access to their, so we say, cookie repository that they've got locally. All you will see is the cookies specific to that domain, right? Or subdomains if they've been flagged that way. Like, so for example, you might find that portal.nottingham shares cookies with my.nottingham or email.nottingham or something like that. In general, that's what you've got. And remember, you can only get cookies that are marked not as HTTP only, right? So if your cookies are marked HTTP only, right, which is not relevant to this answer, but I'm just saying, then you won't be able to access them from JavaScript. Right? It's worth noting that although this question is specifically about cookies, you can do lots of other things with cross-site scripting. So, for example, put CoinHive mining software on them, or send them to an exploit kit, which then puts an Adobe Flash exploit on their machine and then takes over their machine, and so on. Okay, describe in detail how you would attempt to poison someone's ARP cache. Right, and let's deal with the second part later. So, okay, so poisoning someone's ARP cache. Right, so if you recall, on the network layer, you've got sort of IP packets and TCP packets, right? And what they're doing is handling, you know, where you're going from and where you're going to over, let's say, the internet, right? And TCP is handling things like handshakes and then sequence numbers and ports, and things like this. At a very low level, between your machine and the next switch, or the next switch and the next router, you have Ethernet frames. Ethernet frames are MAC address to MAC address. It's just like the most local thing. It's like if your post, it's like in a raw mail situation where you've just got the guy getting the mail out of the thing and putting it in the van. Like one small hop, that's what Ethernet frames are like. So, what you want to do in an ARP cache poisoning attack is trick someone into addressing Ethernet frames to your machine rather than to another machine. So, for example, what you might have is you might have a router here, right, and you might have some other client here, right, and he's got a MAC address, let's just call it MAC1, and he's got a MAC address MAC2, and this is an attacker, right, who's got MAC3, right. Now what you're going to do is you're going to send a you're going to send an ARP response or an ARP reply to these two machines to say, I control. So this is like, let's say this is 192.168.0.3 or something like this, and this is 0.2, and this is 0.1, right? So you're going to send a message to this router and saying basically that I'm 0.2 and I have this MAC address here, MAC3. So I'm writing small for you guys at the back, right? So you're going to send this router a message that says this MAC address is attached to this IP. And you're going to send this client a message that sends this MAC address is attached to this IP. So they now think that the IP for each other, the MAC address, is this one, right? Which means on an Ethernet level, you're going to get all the traffic, right? Because typically, switches and Ethernet cards won't respond to things that are not addressed to them. So then, for example, this client wants to send, worse still, by the way, is they then put them in the cache, right, like this. And so, this is going to last for hours, possibly, right, or until they disconnect from the network and reconnect later. So, what can then happen, So, supposing you were successful, give an example of an attack you could mount based on this. Well, pretty much anything, right, is going to get you marks for that. Because once you've done this, every single message from C to R is going to go via your machine. Right? You redirect it, you readdress it, and then you send it on. But you get to read it. So you can inject yourself as a man in the middle in almost every protocol handshake. You can rewrite DNS requests and do a DNS spoofing attack. You can sniff passwords. Basically, name an attack, you can do it. Right? Okay? Possibly not, XSS, because that doesn't really make sense. Right? So name a network-based attack and you can do it. Right? Hopefully that's fairly clear. So what I want you to say for this kind of question is describe this process, right? You don't have to draw a diagram, but describe that you're going to send an ARP reply to two parties to tell them that your IP, their IPs, their alternate IPs, have your MAC address, right? And that's going to convince them to route all Ethernet packets to you, which you then forward on, having read them or manipulated them or done whatever you like, right? And you also want to mention, because it's an ARP cache poisoning attack, right, that they're going to cache these values and hold on to them for a while, right? So you don't have to do this every message. These get cached, and you can just do it. You can just then use that from then on, right? Have a look at the tool Ettercap on Kali if you'd like to have a go at this. At home. Okay. Any questions about ARP cache? Yes. I believe there is. I couldn't tell you what it is, but I think you type ARP -A or something like that. You know, yeah, there is. Now, if you do that, what's going to have to happen then is your machine's going to have to make a load of ARP requests to find out who's back on the network, at which point they can attack again, right? So a vigilant attacker could prevent, you know, but if you leave a network, then flushing a cache and coming back would be a good idea. Okay, give an example of a low and slow Delana service attack. Right, so slow Loris, or are you dead yet? Right. Now, I only talked about these briefly, but I'll explain to how slow Loris works. So a slow Loris is called a low and slow because essentially it's not a typical denial of service attack where you just send as much traffic as you can to some opponent. Right? Instead, what you do is you abuse essentially a problem in things like how Apache has been designed, where if you don't terminate an HTTP request, they can't really do anything about it, right? Or at least that's what it was like, you know, a few years ago. So you would send. So normally, when you send an HTTP request, you're going to say something like HTTP get 1.1 index.html, and then you're going to send 2 carriage returns. And those 2 carriage returns signal the end of that request, and that's when they respond with a reply, which gives you index.html, right? Or 404, or whatever else they want to give you. Now, if you instead never send those carriage returns, then they might be expecting that you're going to send some other important information, like I want index.html, but also here's something else, like a cookie, or something like this, right? Or here's some information on the browser I'm running, right? Because these things are also attached to HTTP requests. Now, so there's no real reason for them to close the connection, at least for a while, right? And they'll have some timeout, let's say a minute, where they go, okay, fine, this request is clearly not going to finish because he's been disconnected from the internet, right? He's pulled out his Ethernet cable by mistake, and that's never going to happen. So what you do instead is you send 1 byte every minute, right? So you have an HTTP request, HTTP get 1.1, index.html, and then null, or something like that, or space. And it's convincing the server that you're still there, but only enough that it doesn't close a connection, not enough that it actually terminates a connection and sends you a response, right? So in something like Apache, what's going to happen is it's going to keep open one of its connections for you, right? And Apache will have some connection limit of, let's say, 200 concurrent users, right? Which normally is not a problem because you get a request, you immediately send off a response, and then you close that connection and you can accept the next request, and so on, right? No one has to wait very long. It all works really well. But if you keep that connection open, it's trivial just to completely lock that connection out, right? And then you can just do this for 200 threads, and you completely shut down that Apache installation, right? Now, the reason that Apache had a maximum of 200 threads is because it spawns a new process for every connection, right? Now, I don't know why I did that. That's just how they designed Apache. Nginx doesn't do that. So other web servers are not vulnerable to low and slow because they can just have 10,000 connections open because it's just all part of the same memory and they don't really care. If they're not doing anything, it's not using up many of their CPU resources. It's not really a problem. But Apache was particularly vulnerable to this because of basically the core way it was designed. Okay, so that's what a low and slow is. Rudy, or Are You Dead Yet, is exactly the same. It's just that instead of an unfinished HTTP request, you're making an unfinished HTTP post, where you're saying, I'm going to post you 202 gigs worth of data, and then you never send it, apart from 1 null byte at a time, right? Exactly the same. It came around like 6 months later because it was an obvious follow-up to low and slow. So, a low and slow attack, you could give an example of a slow Loris or Are You Dead Yet? Describe its operation, so what I just did, but obviously a little bit more briefly. I'm looking for key points like unfinished HTTP requests, keeping up too many connections, sending bytes every now and again so that the connection doesn't time out, this kind of information. Right. Okay, now the next part of the question, would a stateless or stateful packet filter be effective in preventing this attack? Well, I guess the answer to me is that a stateless packet filter will be no effect at all, right? Because it's just a normal HTTP packet. There's no reason, on a normal port, there's no reason to think that it's malicious because there's no awareness of what the protocol is. Right? Stateless packet filters don't have any information on what HTTP is or why it's useful or how it's used. They just have, it's coming into this IP, which is our web server, on port 80, that's okay. Right? So a stateless packet filter is going to do absolutely nothing to stop this. Right? Theoretically, a stateful packet filter could have some kind of awareness that this connection's been going on too long. Or it could have awareness that this same person has 200 connections open. Right? And if it did, maybe it could intercept that information. So I guess the answer for a stateful packet filter is maybe or yes, depending on how it's configured. Right? And you just give a sentence on why that is the case. Right? So stateful, maybe. Stateless, no. Okay. Right. Good. Oh, we've got just enough time for a bit of fun cryptography. Right. Okay, what is Kerckhoffs' principle, and how does it relate to modern cryptography? Kerckhoffs' principle is the idea that if everything is known about an algorithm except for the key, you can't break it. Right? Pretty much. So it relates to modern cryptography because we don't try and implement cryptographic algorithms with security through obscurity. Right? The idea is not that I've developed this really cool cipher, I'm not going to tell you how it works, and that'll mean it keeps nice and secure. Right? That's not what we do. What we do instead is we create secure algorithms that are secure even though I've told you exactly how they work inside. Right? Because it's much better that way. At some point, someone's going to reverse engineer or find the source code for one of these ciphers, and if it's only secure because we didn't know how it worked, then it's going to be broken. Right? So the Caesar cipher is a classic example of security through obscurity. Right? If you know how a Caesar cipher works, it's utterly trivial, even for someone who doesn't know how to read properly, how to break it. Right? But for something like AES, we all know how AES works. We've attacked it all the time, and we still can't do it. Right? Because that's how it works. So that's the idea. So I just want you to say something along the lines of what Kerckhoffs' principle is, right? And then it relates to modern security because typically what you would do is publish the information on your algorithm and essentially invite attackers, right, to test it. And if it survives those attacks, we know it's secure and we use it. Right? That's how it works. AES was attacked a lot before it was ratified as a standard because they published it. Anyone that tries to publish a cipher and hide away the inner details is going to be in real trouble. This has something also, it kind of relates also to nothing up my sleeve numbers, which are this idea that you don't have constants in, for example, hash functions that you've plucked out of seemingly nowhere, right? Because no one trusts those things, right? So if I say that you initialize my hash function or my random number generator with this value, but I'm not going to tell you where I got it from, that's a big red flag that I've designed that value for some kind of backdoor or something dodgy. Okay. Right. Briefly outline the 3 defining characteristics of the advanced encryption standard. Now, I'm not sure whether it should be the 3 or 3. It depends on how many things you think are defining characteristics, I suppose. But I will just say a bit about AES. Right? So AES is a 128-bit block cipher. It can have 128, 192, or 256-bit keys. It's an SP network. Right? It has 10, 12, or 14 rounds, depending on how many keys it has. So what are the statistics of AES, basically? Right? These are the defining characteristics of it. Right? When I answer that question, that's what I'm talking about. Okay. In what one important way does it improve on DES? Anyone? It has a much, much longer key. Right? DES has a 56-bit key. That is awful. The minimum AES key is 128 bits, which is uncrackable. Right? You can't brute force through 2 to the 128 values. Okay? So that's I mean, it also improves on DES because the round function is a little bit stronger. But that, I mean, and I'd probably give you the mark for that. But that's not what I'm interested in. I'm interested in the core improvement, which was the key. DES was deprecated specifically because it had a short key. Right. Okay. Right. In what way are stream ciphers vulnerable to message tampering? Good question. So a stream cipher is vulnerable to message tampering because essentially the encryption is only XOR. So if you remember, what we have is we have some kind of key, right? And we have maybe a nonce up here, right? A number used once. For those of you who've forgotten, these come into a key stream generator. Key stream generator. That kind of didn't work because I didn't fit it in. Right? And this produces key bits. Right? So this is key 0, 1, 2, 3, ... Right? And that's going to be random, right? Or at least pseudo-random, so we can't guess what it is. It's very important in a stream cipher, remember, that we can't guess what these are going to be. So, the message comes in here, right? And we XOR it with the key bits, 1 bit at a time. And that maybe flips a bit, maybe doesn't flip a bit. We don't know, because it depends on the key. Right? And out comes the ciphertext. Now, this is secure, because if you take this key stream away, we don't know whether these bits were flipped or not. So we can't map between these two things. Right? So that's why it's secure. But it's not it's not impervious to message tampering. Because let's imagine that if we have a message here, 0, 0, 1, 1, 0, right? And this leads to some ciphertext, 1, 1, 0, 0, 0, right? XOR, if you change one of the inputs, the output flips. Right? That's how XOR works. So if I change this, let's say I intercept this message and change this to a 1. This works better actually if we're on decryption. So let's swap this around. Right, so I'm decrypting the message, the ciphertext, because the decryption is exactly the same, remember? Right, it's the message. So I'm an attacker. Right, I know this is a bank transaction. I can't read it because this doesn't make any sense. But what I can do is change that 1 to a 0, and then this 0 changes to a 1. Right? Now, that's not good. Right? Because if I do that, that could be the bank account that the money's being transferred to, right? Or something like this. So, on its own, a stream cipher can't protect from message tampering, and it's even easier because in a block cipher, if I change one of the bits, the whole block gets messed up. Right? If you change one bit in a block cipher, the output's going to be total nonsense. And yes, it's messed up the message, and that's kind of a denial of service, but the victim is going to know, well, that block makes no sense, I'll just ask for it to be sent again, or something like this. Right? In a stream cipher, there's no way to tell that it's been flipped, because the message comes out fine, it decrypts, right? And it could be your message makes no sense, but it could be you flip the exact bits where it does, right? You get a sort of location-based attack that you can do. Right? Now that's a lot more verbose than I need for that many marks, but right? Write some subset of that and you'll be fine. So, how does the message authentication code protect message integrity in this case? So the issue is message integrity. Someone could alter this message, and crucially, I wouldn't know that they'd done so. Right? And that's a really big problem. So what a message authentication code does is you take the ciphertext, right? You send it off. So this is your ciphertext message. You then take the key and you append it to your ciphertext, and you hash this. Something like that. I mean, my writing's bad. So you hash the key in the message, or you perform an HMAC or GMAC or any of the above. Right? And what this means is that if anyone flips any bits in this ciphertext, this hash will no longer match because you haven't been able to flip that bit in there. Right? And so it's immediately obvious if someone has tampered with this message. And at that point, you ask for the message again, or you tear down the connection or throw a warning, or whatever it is, depending on your use case. Right? The reason they can't produce this hash a second time is because they don't have this key. Right? If you were just doing hash of the ciphertext, that's no good, because you could just flip this bit as well and then hash that and recompute the hash. Right? So we don't do that. What we do is we append the key and then hash that. Right? Or in HMAC, we append a half of the key and hash twice. Okay? So that's what a message authentication code does. I'm interested in message authentication information to that level of detail. I'm not interested in exactly the nature of the bits and how you're appending things together, because it would depend on the implementation. Okay, I've just about got it. Let's just see if I can knock out this last ridiculous on question in 5 minutes. So a web server uses RSA key paired to verified center. By signing messages. It's kind of like padding text. By signing messages with a private key D. Okay, so what happens if an attacker... you have to get a whole sentence in before I get to the point. If an attacker was able to determine the private key, they'd be able to impersonate a server. Explain how the private key can calculate from the public key. Right? That's the key to this question, is if a server... It's basically saying, look, getting a private key is really bad. Right? How would they do that? Right? Well, let's see. So, and you might have forgotten, right? But this is something you can work on over Easter. So, as an attacker, the public key, E-N. Right, that's what you know. And the question is, how do we get D? Right, given those things. Okay, so let's first discuss how we would do it, and then we will discuss whether it's practical. Right? So the first thing is, we know there's a relationship between E and D. Right? The relationship is that E times by D, right, mod the totient of N is 1. That's what we know. So we know E and we know N, right? So to solve this equation using, let's say, the extended Euclidean algorithm, all we need to know is the totient of N. So the question then becomes, can we get the totient of N? This is the totient of N here, right? The totient of N is all the numbers between 1 and N minus 1 that are co-prime with N, right? Or their greatest common divisor is 1. Right? Rewatch my slides. Now, can we do that? Well, the formula for... We could brute force this. So we could say, right, is the totient of N... we could calculate the number of numbers between 1 and N minus 1, for which this is true, and add them all up, and that would be the totient of N. Right? But that would take ages, because N's 2,000 bits. So let's not do that. Let's instead use the formula that we know, which is the totient of N is equal to P minus 1, Q minus 1. Right? Okay? We know that formula. So now the question becomes, do we know P and Q? Well, no. But we do know that N is equal to P times Q. Right? Because that was used in the key derivation phase. Right? So now the question becomes, can we tell what P and Q are? Right? Can we? Anyone? No. Right? P and Q are 1,000-bit prime numbers. N is a 2,000-bit semi-prime number. This is the integer factorization problem, and for numbers of that size, it's totally impractical to do. Right? That's the answer to the question. That, and then no. Right? But I do want you to mention, preferably, that the numbers have to be big for this to be secure. The answer is, can we solve this? Is if N is 10 bits long, yes. Right? So it only is secure if the numbers are big. Right? That's very important, right? Which is why we have N's of 2,000 bits or 4,000 bits. Right? So this is how you calculate a private key from a public key. You factor N into P and Q. You use this formula here to work out what the totient of N is. Right? And then you apply the extended Euclidean algorithm, but you don't need to mention that by name. And just say you apply this formula here to calculate D given E. Right? And then it's trivial. Right? So if you know P and Q, it's completely easy to do this. It takes a second or so, but it's very easy to do. If you don't know P and Q, you've got a real problem, because you're not going to know what the totient of N is. Right? That's the answer to the question. 7% of the module mark is just for doing that. Revision. Okay, what I'll do is I'll maybe cover a Diffie-Hellman question, etc., next time after Easter. But if you get stuck on things, do let me know, and I'll try and put some answers up on the on Moodle. Okay. Hi.